Okay, we're now going to talk about a controllability problem, and we're going to put the ideas we introduced last time on the least norm, least squares problem into practice to solve an optimal control problem. But before we get started, I think I should probably warn you that this is going to get pretty tricky. So be prepared to really take your time and try to understand these ideas. We're going to see quite a lot of advanced concepts very quickly, and if you can master them, you will have an incredibly powerful tool at your disposal, but do not be disheartened if you find it confusing the first time you see it, because it's hard. But that's why it's interesting. So what are we trying to achieve? So we have a state space model, a linear state space model as normal. And now say we have an initial condition. Suppose we've got a two-dimensional state space here. We're at the point x0 at time t is equal to 0, and we want to drive our system to arrive at the origin at time capital T. So this is what we want to do, and we'll just assume that our system is controllable, and we saw when we were discussing controllability that, in fact, if a system is controllable, there are lots and lots of ways, lots and lots of inputs that we can apply to our system that will take us from x0 to the origin. So maybe one of them will take us along some path that looks like this, another one along some path that looks like this, another one on some path that looks like that. So we have all of these possible inputs that will take us to the origin. Which one should we choose? And we're going to choose one to optimize a criterion. So we are going to try to pick the input that minimizes the energy required. And so let's say what we're actually trying to do. We want to minimize the energy, and of course for this actually to correspond to energy, we would have to attach some physical meaning to the variables. We're not going to do that, but often when you look at energies, you get things squared. So if you look at energies on capacitors or something, you get voltage squareds and so forth. So this quantity here is often used as a kind of a general concept of the energy in a signal. And if the units of the signal are right, it will correspond to energy. And here I'm going to have U transpose. So this is transpose. This is capital T. U transpose of T. U of T dt. So we want to minimize the amount of control input that we use, subject to the fact that we arrive at the origin at time t is equal to capital T. And if you remember the lecture where we talked about exactly this problem, we found that this condition corresponds to, so subject to, and this is the condition that's enforcing the fact that we arrive at the origin at time capital T, subject to the fact that minus x0 is equal to integral from 0 to t, and then here we had e to the minus a t b u of t dt. So I encourage you to look back at the lecture on controllability tests to remind yourself why this needs to be satisfied if we're to end up at the origin at time capital T. But for now, let's just take that as a given. So we want to solve this problem. We want to minimize the square of the input signal subject to the condition that we arrive at the origin at time capital T, which corresponds to this equation here being solved. And what I want you to start to do is see parallels between, let's just divide some things off, between this problem and the least squares problem that we studied for matrices last time. So if we just relabel the variables, the least squares problem that we saw last time, well, we looked at argmin, but we looked at minimizing the norm of some vector u subject to the fact that y is equal to mu. We use slightly different variable names for this. Last time we had u x instead of u, and we had a matrix A instead of M. We're just switching them to try to minimize confusion with the state space variables. So this was the least squares problem that we saw last time. And I now just want you to sort of think of this problem in exactly the same terms. So how are things different? Well, the most obvious way that things are different is, it's good practice. Maybe I didn't do this last time, but it's good practice to always say what you're minimizing over. So what's changed? Here we had u was a vector. It was a vector, so an n-dimensional vector. And here u is a function. But if we think about it, there's really very similar things going on. So if we sketch this out and say that we've got time and this is capital T, so some signal u might look like that. So this is u of t, but we could certainly approximate this with some vector u. We could just, and by increasing the dimension of the vector u, we could kind of describe whatever function that we wanted, u of t. So I'm sort of imagining that these here, u1, this is the first entry of a vector u, u2 is the second entry of a vector u. And just by having more and more and more and more dimensions in my vector, we could get a better and better and better and better description of this signal, u of t. And provided that you normalize things correctly, in fact, the length here corresponds exactly to this integral here. So this is, if you like, a kind of an infinite dimensional version of u, where we have a function instead of a vector. So we've got something that sort of, we've got a sort of correspondence for our vector slash function u. And how about the constraint? Well, this is also kind of like a linear constraint. So I want you to think about this in exactly the same way that we're thinking about y is equal to mu. And if you draw out this integral, like if we take this perspective here, it's the same as just chopping up this e to the minus atb into lots and lots and lots and lots of pieces and putting those into the columns of the matrix M. And then this multiplication, if you like, becomes an integral in the limit that we have. We divide our u into an infinite number of pieces. So it looks like we've got a very strong parallel between this problem here and the least squares problem that we saw before. We're just dealing with different spaces. So let's just write a few more details. So in this problem, in the problem that we saw before, u was a vector and y was a vector. Here, our output's a vector, and our input is a function, so it's like an infinite dimensional vector. But the equation is still a linear equation. So we have a linear equation. M is linear. It's not going from vector to vector. It's going from function to vector. So the way we could write that is we could say that the M in this case, or in the case of this problem here where we're trying to find the input with the least energy to drive us from x0 to the origin, this function, it takes, and a kind of a fancy way to write this, it takes L2, I don't know, there's lots of ways to denote this. Let's do it like this. So this is the space of square integrable functions defined on the interval 0 to t. And that's just a kind of a fancy way of saying the functions that are defined on this interval of time between 0 and capital T, which have finite norm. So That's all this is. This is like our function analog of the vector u. And so our matrix M takes one of these functions, and what does it turn it into? Well, if we perform this integral, we get a vector. So given any input function, the effect of acting our linear operator M on that input function, it will yield some vector. And the fancy way of writing that is like this, but this just means n-dimensional vector. So kind of the point of all of this is that we still have a least squares problem, and in fact we can use the least squares solution. And I'm just going to spend the rest of this mini lecture explaining how we would compute that least squares solution based on, we've identified what M is. M is this. So what M does is it takes any function and it produces this, it performs this integral on that function, and it produces an output in the same way that a matrix takes any vector input and produces another vector output. So I'm going to describe how we would construct the least squares solution from this object here. I also encourage you. Last time we did the derivation of the least squares problem, and we did it by essentially we identified this orthogonality condition, and then we showed that by substituting in this least squares solution we satisfied the orthogonality condition, and then we proved that any other solution will necessarily any other feasible solution will necessarily have larger norm. And you can actually repeat all of those steps with the solution I'm going to give you. So and maybe that will help you to gain a bit more trust in these methods. I mean, maybe you, and quite rightly, you would not be convinced by me just saying, okay, least squares still works. All we have to do is compute that least squares solution in this more abstract setting, and it will give us the answer. But you can, in fact, take the optimal solution that we're going to derive now and go through exactly the same derivation, but with the appropriate norms, and see and verify it through another method that this does, in fact, give the optimal solution. Any other choice of input function will necessarily result. Any other choice of input function that drives us to the origin will necessarily have a larger value of this norm here. So we have a least squares problem. We sort of understand the connection to the least squares problem that we saw before. And we have a least squares solution from last time. We know that our optimal solution, so maybe I'll shove it in here, is so the minimizer, so the argmin of this, u star, is equal to m transpose m inverse m y. We've identified what m is. In fact, the only thing that we need to do in order to compute this solution is to find m transpose, or the analog of m transpose. And the way to try to work out what m transpose is to look at inner products. So I'll now sort of explain what we need to do. So let's just, again, just think about things in the matrix setting. So let's look at y transpose y. And this is equal to y m u, and y transpose mu. And in sort of fancy language, you would say this is an inner product between the vector y and the vector mu. But that's not the only way to think about this. So we could think about this as the inner product of this vector and this vector, but we could also think about it in terms of the inner product between m transpose y transpose u. And so if you think about it, these are actually, in this inner product, we're doing an inner product where I group things like that in the output space. And in this one, we're doing an inner product in the input space. And we can use this idea to actually define what our transpose is. So we know the space in which our inputs live and our outputs live. So we know what the inner products correspond to. And we can use, we know what M is in this case, and so we can use this to actually define what M transpose is. So I'm just going to go through the steps now and point out what M transpose is in this more abstract setting. And once we've found M transpose, we just need to compute the least squares solution. So, and I think I have even written down the wrong, yeah, that's the wrong least squares solution, isn't it? It's actually, let's just get rid of it. The least squared solution is U star is equal to M transpose M transpose inverse Y. Okay, fine. So this is how we can define the transpose. What's this going to look like in our setting? Well, we'll start with Y transpose Y. So what is that here? So that's equal to X naught transpose X naught. And what does that equal? Well, we have our conventional interpretation. So if we do our inner product in the output space, so our output space is just the n-dimensional vectors. So here we have minus X naught transpose, and then integral 0 to t e to the minus at b u of t dt. Okay, fine. This is, and then this is just an n-dimensional vector, this is just an n-dimensional vector, and this is our, like the action of our matrix M on the input U. How could we rewrite this? Well, we could pull in the minus x0 transpose, and then we could have, yeah, and then we've got e to the minus a transpose b u of t dt. And now if we just group this up, let's put those back in, 0 t, and now just in the same way that we sucked the m into our transpose here, we're going to do exactly the same thing, and we get b transpose e to the minus a transpose t x0 transpose u of t dt. And so we're almost there. So the final thing that we need to do is confirm that we're comfortable about what our inner product is. And the inner product with these L2 functions, so the inner, you would often write it this way. The inner product of two L2 functions, y and u, maybe let's do x and, let's do the inner product of w and z to make sure we're not using any variables that we've used before. Is the integral from 0 to t of w transpose of t z of t dt. And so just by comparing terms, what is the w transpose of t? Well, it's just this thing here. So what is M transpose? Well, M transpose is exactly this. So this object here, this is our M transpose. And what it does, so in the same way, if we had matrices, and this M went from an n-dimensional space to an m-dimensional, the transpose would go from M to n. And exactly the same way here, M transpose goes from Rn, and it will give us a function defined on 0t. And we see that's exactly what this does. We give it a vector in Rn, and it outputs a function defined on L2 between 0 and t. And this is precisely the inner product for this space, which is just the direct analog of W transpose Z. This is just the integral version of W transpose Z. So we've identified what what corresponds to M transpose. There's actually a fancy name for all of this stuff. So you don't write transpose anymore. You write star. So we'll actually call this star. And in our least squares solution, we don't have transposes, we have stars. And the star here stands for adjoint. So M star is the adjoint of M. M is the linear operator from these functions to these n-dimensional vectors, and M star is its adjoint. And it's defined through moving from we have the inner product in the output space and the inner product in the input space. And one gives M and the other gives M star. But anyway, we found M star for this problem. Which means that in order to compute the optimal input, we just need to substitute into our least squares solution. So our least squares solution says that U star, and now U star is a function, so it's going to be of time, and it's equal to our adjoint. So here we have B transpose e to the minus a transpose t. So that's our adjoint, and this is all multiplied by m star inverse. So let's have the inverse there. And what is m star? Well, m just does the integral from 0 to t of e to the minus a of t. B, and we integrate, and it acts on whatever the input is. And what is the input? Well, the input is M star, which is B transpose e to the minus a transpose t. And all of that is multiplied by y, and our y is minus x0. And now hopefully you recognize this guy. This was the thing that we were calling the controllability Gramian. I mean, technically, actually, the controllability Gramian doesn't have these minus signs in here, but it's got the form of a Gramian. And it's the thing that we call W. So this is the controllability Gramian W defined on the time interval 0 to t. So at the end of all of this, our optimal input is minus B transpose e to the minus a transpose t, W of t inverse x0. And if you look back at the lecture when we were talking about controllability tests, this was precisely the input that we used to prove that condition 3 was equivalent to condition 1. So that shows that that input corresponds actually to the least norm input. It's the input that takes us from x0 to the origin with the least amount of control effort, U. And as we're varying the time horizon t, just corresponds to varying capital T here. We can actually get a little bit of extra insight. So let's actually look at the value of this thing here. So that's our optimal input. What is the energy in that input? Well, if we just substitute this in, we find, and I encourage you to go through the steps, that the integral of U transpose of t, U of t, dt is actually equal to x0 transpose W of t inverse x0. And so we can actually get some insight into the amount of control effort just by looking at required for different inputs, just by looking at, say, the eigenvalue decomposition of this Gramian here. And in particular, if, let's say, x0 is an eigenvector of W of t, and let's say it's the eigenvector corresponding to the smallest eigenvalue of W of t. Well, if that's the case, then this, and if it's normalized, then this is just equal to 1 over that eigenvalue. And so you can see if we have a very small eigenvalue in W of t, we can end up requiring control efforts that go with 1 over the size of that eigenvalue. So something really large. And so the eigenvectors associated with small eigenvalues of W of t correspond to directions that are very hard to control in. Or they require very large amounts of control effort to drive you to the origin. So if we start in one of those bad directions, it will take a lot of control effort to get to the origin. So yeah, okay, that's an enormous amount to take in, and these are not easy concepts. But hopefully you can now see, like, well beyond where you thought you would be able to see, or you see the reach of linear squares, of least squares, goes well beyond that kind of simple matrix. Yeah, that matrix problem that we solved last time is immensely useful in its own right, but these ideas generalize even further. And here we have a taste for how you can use them to solve optimal control problems. In terms of kind of hints for how you can use this and generalize this and use this to solve some of the problems, or the problem on the example sheet. So you always, when trying to set these problems up as least squares, you always want to try and identify what your function m is. So in this case, our function m goes from the set of all signals, square integrable signals on some interval 0t, to a set of real numbers. But suppose we were given a restricted class of signals u of t instead. We can't pick any value of u of t. Say we can only pick a piecewise constant value of u of t, and we can choose the height of this, but u2, u1, something like that. Well, we could, and we want to pick the best u1 and u2 instead of the best function. Well, we just have to set things up and go through the steps in exactly the same way, except this time we'll end up with a mapping M that goes from a two-dimensional space, so the values of u1 and u2, to Rn instead. And you could imagine generalizing this for different shapes of function and all sorts of different things. But the secret is always to, first of all, write down your problem, and then try to identify what your matrix M is, which spaces it goes between. Then identify the inner products in the input and output spaces and use those to work out what your adjoint is. And then step through, compute your least squares solution, and then just substitute everything in, and it should just it'll just give you the optimal inputs. Perhaps you need to compute. We always end up with things involving integrals. So if we ever actually wanted to find this object here, we would have to numerically compute it by solving this integral. There is a case where you can actually solve this algebraically. So in the case that t goes to infinity, subject to some other conditions on the matrix A, you can actually solve this integral algebraically. But in general, you wouldn't be able to necessarily, and you might have to compute some of the objects that pop up numerically, but you can. There are well-defined and good stable numerical routines for doing this, and the framework all applies. Yeah, I think I'll just stop there, I think. But anyway, we have quite an advanced introduction to least squares problems and optimal control problems.